My name is David Dominguez. This is Gianni Jimenez and Genesis Vasquez. Our advisor is Professor George Dulikravich, and we will be doing a reaction control system for NASA's NanoLaunch project. Now, the purpose of NanoLaunch is to build the cheapest possible launch vehicle that can get a 3U CubeSat into orbit. And the motivation for this is so that more universities can take part in atmospheric research and global observation and any other experiments that they need to do, which the results will help the world out as a whole. Now, the current available launch vehicles, you can see here, the space shuttles there just for scale. But the problem with these vehicles is that, one, they need to have a CubeSat deployer, and two, they need to be going to the altitude and inclination required for the experiment. Now, NanoLaunch, on the other hand, since the CubeSat is the primary payload, you can go wherever you want. Now, if you notice here on the NanoLaunch, the first two stages have fins, but the last three do not have fins because the third stage is going to fire out of atmosphere. So to control the vehicle out of atmosphere, you need a reaction control system, which is basically just a series of ports through which you can fire gas that will cause a dynamic reaction of the vehicle. So here you can see like the shuttle flipping upside down using RCS. Now, for us, our RCS will be firing in between stage ignition, so it can align the vehicle to make a tangent to the curvature of the Earth so they can accelerate to orbital velocity.
Thank you. So our objectives are to design a reaction control system that's reliable, cheap, easy to manufacture, and safe. And we're planning to build and test the prototype using, first we're going to analyze our design with computational fluid dynamics, and then we're going to do some rapid prototyping, and then test the prototype, and perform some dynamic analysis in order to So here's our collaboration. We're collaborating with NASA, who's providing the funding and the needs, goals, and objectives for our project. And we're also collaborating with the NAGROC in order to perform the analysis. Here's a small breakdown of our responsibilities. So David is doing the CAD model, and along with Gianni. And then we're going to perform the testing and manufacturing, and then I'll work on the analysis and flow simulations. And here's a timeline that we expect to follow. So the NASA group is already working on their own RCS system, and the issue with that, though, is that their design has several disadvantages. For example, the number of pipe fittings, the number of valves, actuators, and the pipelines are much longer, so it leads to a higher weight, higher cost. So we're working on improving all of these factors.
Thank you, Genesis. All right, from the beginning, we knew we needed to create a lighter and cheaper reaction control system. David came up with this rotary system, and he brought it up to his NASA supervisor. His supervisors loved the idea and told him basically, design it, manufacture it, and test it. Now, some of the design challenges we need to analyze and overcome includes the force exerted on the valve, the bearings, the bracket, and the screws holding the whole system together. The other challenge is that we need to analyze is the vacuum efficiency of the whole system. This means picking the right size and type of O-rings that will guarantee us there's no loss in pressure. Now we're thinking of building three prototypes. One's going to be milled out of Delring, which Professor Sikarides was helpful enough in giving us the input in manufacturing and tooling tolerances. The other two will be the additive manufacturing process. One was printed out of PLA here in-house, and if the project is feasible and successful, NASA will go ahead and 3D print it out of titanium. Now, the advantage of our system is that it uses only one on and off valve actuator, compared to NASA's which has 4. Our system will include less pipe fittings and less pipe materials. Some of the disadvantages we need to analyze is the possible failure in the stepping motor, which controls the rotating valve within the manifold. The other one is that our main components are not commercially available, so we have to manufacture them. Here's a simple design of how our system works. At any given point, cold gas runs through it, and then the valve will distribute it equally to 2 outputs. Our design meets NASA requirements, which needs 4 RCS activation for the thrust to control and maneuver the rocket. Now, our current progress is that we manufacture we 3D printed one out of PLA, and we're going to study the tolerances and use it for first test design with compressed air. We're going to go ahead and start with CFD analysis, and possibly start buying the pipe fittings and pipe materials. Thank you for your attention, and if you have any questions, we'll be happy to answer.
You're going to build a rocket rocket that tested it, or is it just
They actually have one. It's, they have a Class 3 rocket that they've been testing the all avionics and all that on, and this is it. It's about 14 feet tall, and it goes Mach 1.2 up to about 10,000 feet, and so everything's thrown on that first to see if it works.
so your device you'll test it in some form here, and then ultimately it's going to go into one of those?
Right, it'll go into there, and then we'll measure the force generated when it's in flight.
Yeah, what controls the gas that's being emitted through the nozzles?
There'll be an on and off valve feeding into the inlet of the valve,
Right.
and then a stepper motor will control it from the other side to move it to the proper ports.
And how does it know which is the proper port?
The stepper motor will be calibrated, so it knows exactly which.
So
it'll know what
gyroscopes
angle
or
to
anything
move
like
it.
that? I mean, how does it know the angle that it's at?
It'll be calibrated initially, so once you set the calibration, it'll know exactly which one to go to. So if it needs to pitch, it knows to go to whatever angle is set on it once that's calibrated, and that'll be set in code.
Okay, but I still don't get, the sensor is gyroscopic? I mean, how does it know what attitude it's on or rotation?
Oh, because there are gyroscopes.
Okay, so it does have gyroscopes on there?
So it's a computer.
Okay,
The computer will direct the motor to
all right.
turn that valve.
Okay. The question I ask is there really only binary output? You either pushes gas out top to bottom or left to right, or do you have the ability to do both left to right and down, up and down at the same time?
Well, these are the only combinations that this valve can do right now. If for some reason they need something else, more ports can be added and more combinations.
Because the question I really ask there is that adequate? You know, obviously they have 4 today, so that they can probably run multiples at the same time. So now all of a sudden, instead of just
Angle.
going up or sideways, they've got the ability to make the orientation changes.
Well, because if you needed to pitch, you know, you would rotate the rocket to be so that, you know, the top left one there. But if you needed to yaw, you would rotate it sideways and then activate it.
But you can't do pitch and yaw at the same time.
Right, no, you
So it'll
wouldn't.
do
And
two
now, and
steps.
so now how am I going to get to someplace that I'm trying to get to?
Well, yeah, I mean, you would yaw then pitch, and then, because you have about 2 minutes in between the stage firing, so you have plenty of time to align it however you need, so there's no real rush. And we're also going for the cheapest, simplest possible way to do this, so if you add it to, you know, be able, I mean, most modern, you know, $100 million rockets can, you know, do those multiple changes at once, but that adds cost and complexity, and we're just trying to figure out how to do it the absolute cheapest, most simplest way.
Would this rocket have more than one of these devices in it? One fore and aft, or?
As of right now, they're saying that it only needs one in between the third and the fourth stage.
We have more questions?